So 4, 5, we started logs. We actually got to all the stuff that's on this warm-up. So we're going to go through the whole thing, and then we'll finish the last couple examples that are in those notes. Okay, but there was a couple of different types of problems within the logs, right? So there was either exponential or log. With exponential, there's two kinds. One where you can change the base to be the same number, and you do that, get the exponent, set them equal to each other. That's using the one-to-one property. The other where you couldn't change the bases to be the same, and so you had to take the log of both sides of the equation. So if I look at 1 and 2, 1 is like the first kind, right? Can I rewrite 2 and 8 to have the same base? How? Good. So 4 could be 2 to the second, right? Raised to the 3x minus 1. And then 8 could be 2 to the third, raised to the x plus 1. And then I can take my exponents, which are now the same. I can say that this equals, or the bases, which are now the same, sorry. So I can take the exponents. Distribute this 2, and I get 6x minus 2 equals, distribute the 3x plus 3. Subtract the 3x. 3x minus 2 equals 3. Add the 2. 3x equals 5. And then divide by 3. And I get x equals 5/3. Raise your hand if you got it right. Okay, good. All right, so 2 is the second case where I cannot change 20 to be a power of 3. And I can't write 3 as anything other than 3. So this is the one where you want to find the ln of, or log, sorry, of both sides of your equation. So I'm going to say that the log of 3 to the 2x minus 1 equals log of 20. And then I take the exponent, bring it forward. So this is 2x minus 1 times the log of 3 equals the log of 20. Divide both sides by the log of 3. I get 2x minus 1 equals, excuse me, log of 20 over log of 3. And I can either find that now and round it, or I can keep going. So I could add the 1. 2x would equal log of 20 over log of 3 plus 1. And then the last thing I'm going to do is divide by 2 at the end. So I can do that all at once in the calculator, or I could break it down into its parts. So I would find the log of 20 divided by the log of 3, and I get 2.726. So if you rounded it there, you could have like 2.7. Then add the 1, 3.7. Then divide by 2, and you should get 1.86. I don't think it's set to round 1, so I'm going to round to the nearest tenth. I'm going to say that x equals 1.9. And both of those you can check. You can plug them back into your exponents and make sure that the left, it may not equal exactly the right because we're rounding, but it should be pretty close to it. Questions on either of those? So the exponential, Karina.
So when you set the equations equal to each other, why do you put 6x minus 2 to the 3x plus 2?
So I took the exponents here. Like once the bases are the same, so the 2 and the 2, this was 2 times 3x plus 1, and this is 3 times x plus 1. So then I just distribute it. Any other questions before we get into the log one? Okay, so 3, then we got into log. So there was a couple of different things. One case where there's a single log on one side of the equation, and so in a situation like this, I want to get this into exponential form. The other was if there's more than one log, so I would condense it on the one side of the equation, then get it into exponential. And the third case is if there's a log on either side of the equal sign, and then I can use that one-to-one property just like I did with the exponents. So in this case, I would be getting this in exponential notation. So the 7 comes over here, picks up the 3, 7 to the third, drops off here, equals 5x plus 3. 7 to the third is 343, equals 5x, or plus 3, sorry. Subtract the 3, 340 equals 5x, and then divide by 5. X equals 68. And just like with the exponential ones, I can take that 68, plug it in, 5 times 68, add the 3 to it, and then check to make sure that log of that number over log of 7 would give me 3. So both of these can be checked.
Why do you change it to 7/3?
So when you put it into exponential notation, the base comes over and picks up the exponent. Oh, say that again. Why? Yeah.
Why did you change it to that log?
So in order to get it out of log into exponential, that number picks up the number on the other side and drops off. I've got to get rid of that log.
And you do that for all of them?
Anyone that has a single log. Yep. Any other questions on 3?
Like whatever numbers is small.
Whatever that little number is, yeah. So then 4 has 2 logs on one side. So I have to condense these to 1, and that's a minus sign, which means what? Divide it. So this would be log of 3x plus 1 over 4 equals 2. Now I've got the same case I had in the last one where I have 1 log on one side of the equal sign. So I've got to get this into exponential form. What's the base on that log? 10. So this is really log base 10. So the 10 comes over, picks up the 2. 10 to the second equals 3x plus 1 over 4. If you're better at seeing proportions and cross multiplying, I can add the over 1 here now. And then this would be 100 over 1 equals 3x plus 1 over 4. And I can cross multiply that. 4 times 100 would equal 3x plus 1. Continuing down here, 400 would equal 3x plus 1. Subtract the 1. 399 equals 3x. Divide by 3. And x equals 133. So the goal there was getting it to be in one function, like condensing the 2 logs into 1, and then you can either multiply by the 4 on the bottom and then solve it, or you can put it as a portion, whichever one makes the most sense for you, and cross multiply. And then just like before, I could take that x and plug it back in, that 133, and when I do, I should end up with 2 on the left-hand side of the equal sign. Questions on that one? All right, so we're continuing the 4.5 notes. So we talked about x functions, we talked logarithmic functions. We left off with this one. So it says solve and check. I've got 1 log on one side of the equal sign, which tells me I'm going to do what? Put it in exponential, right? So this 5 comes over and picks up the 8. 5 to the 8 equals x to the 4th. Okay, then I'm going to use my calculator to phrase 5 to the power of 8, because I don't expect you to do that. That would be pretty brutal. And I get 390,625 equals x to the 4th. Now how do I get rid of a 4th power? Take the 4th root of 390,625. And I want to find the 4th root of 390,625, which is 25. And then it says to check it. So if I plug 25 back in, I would do 25 to the power of 4, which gives me that 390,625. And then I would do log base 5 of that, or I would do log of 390,625 divided by the log of 5. And I should end up with my 8. Is there any other way you could have done this? Can you think of any other way you could have done it? What can we do with exponents on logs? You can push it to the front. So I could have taken this exact thing and wrote 4 log base 5 of x equals 8. Now before I can put that into exponential notation, the log's got to be by itself. So I've got to get rid of the 4 in the front. That is 4 times log base 5 of x. How could I get rid of that 4? Divide it by 2. Or sorry, divide 4 on both sides. and I get log base 5 of x equals 2. And now, can I get that in exponential notation a little bit easier? 5 comes over, picks up the 2. And x equals 25. So the thing with all of these exponential functions, all the log functions, is all of your properties apply. So there's a lot of times where there's more than one way to do it, and it's okay. Okay, you could do it more than one way.
Since like one way was like ridiculously hard and then was easy, are we still gonna have our calculators for it?
Yeah, you'll still have a calculator.
Okay.
Yeah. Okay, so this is the one that's kind of like the warm-up. So I've got 2 logs on one side of the equal sign, which means I want to condense, right? So if I'm condensing and it's addition, what happens? I multiply. So this becomes log of 12, or log base 12 of x times x plus 1 equals 1. Now I have 1 log on one side of the equal sign, which tells you you're going to do what? God bless you. You can distribute it now or in a step or two. It doesn't matter which one. Yeah, eventually you're going to distribute that in. Okay, so you both answered good questions. So 12, I'm going to put an exponential. 12 comes over, picks up the 1, and I get x times x plus 1. So either I do it at the beginning or I'm going to do it now, but at some point you're going to distribute that x. So this would be 12 equals x squared plus x. And then as soon as you see an x and an x squared, hopefully a red flag goes off that this means you're going to have to factor. So you want to get everything to one side, and I usually want to keep the x squared positive, so I'm going to move the 12 over to be on the other side. And I get 0 equals x squared plus x minus 12. And then I factor this. So what are the factors of negative 12 that sum to positive x, or positive 1? Good. Positive 4, negative 3. Which means I set each of these equal to 0, and I get x equals negative 4 and x equals positive 3. So here's the catch to these, and this is why they're different. When you end up factoring with two answers, you have to check these, okay? So they all say solve and check, and sometimes it's really just to check your work. But when you end up with 2 answers, when you end up with something quadratic like that where you factor and you end up with 2 answers, there could be an extraneous root. And you won't know it unless you check it. So I'm first going to take the negative 4 and I'm going to plug it in up here. And I get log base 12 of negative 4 plus log base 12 of negative 4 plus 1 equals 1. So I'm checking the first one. Yeah, there is. It doesn't happen often, but there is. Okay, so if I go to do this in the calculator, first of all, some of you have change of base that you can type that right in, but the rest of you would have to write this as log negative 4 over log 12. And if you do that, so everybody try that right now, log negative 4 divided by log of 12. What happens? You get an error. So you cannot find the log of anything that is less than or equal to 0. So if you're trying to find log of 0, it won't work. If you try to find log of negative number, it won't work. Which means I already have eliminated this root. So if I go to plug it back in and I end up with log of a negative number or log of 0, then it's not a solution. It's called an extraneous root. So let's say it worked for here but didn't work for here. I would still eliminate it. So if at any point I end up with log of 0 or log of a negative number, then I would rule that root out. So now let's try it with the positive 3. So this time this is log 12 of 3 plus log base 12. 3 plus 1 equals 1. So now I would do, again, unless you have the change of base, you're going to do log of 3 over log of 12. So this was 12. And then I would do, so log of 3 over log of 12 plus log of 4 over log of 12. And that should give me 1. So if I do that in the calculator, log of 3 divided by log of 12, which is like 0.442, and then log of 4 divided by log of 12, and I get 0.557. Add that to that 0.442, and I get 0.99998, which is pretty close to 1. You could do the same thing. Yeah, no, it's the same thing. So you could check it either way. The thing about the quadratic ones is either you're going to be able to find the log or you're not. If it's an extraneous root, when you plug it back in, it will be negative or 0, and you won't even be able to get past that point. Does that make sense? Okay. Questions overall on any of that? So when you deal with it, when you're factoring, those are the ones that you have to check to rule out an extraneous root. The other ones you're checking to make sure you're right, but these you're checking because you can rule something out. Ian?
So when you said if one of your answers is less than or equal to 0, it's obviously...
If when you go to type it into the calculator and you get log base whatever, and that large number is negative, so you can't just say negative in general because, okay, so let's say I had log of x minus or plus 2, right? Plus blah, 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 whatever it is. And let's say I go to solve it and I get x equals negative 1. So the negative 1 itself, when I plug it back in and I add it to 2, becomes positive. So it's not that it's just any negative or zeros. It's that when you plug it back in and you simplify what's in here, if whatever's there is 0 or negative. Does that make sense? So you can get negative roots, but you can't. And you know what, Bradley, going back to what you said, it might not happen often, but let's say at this point, this was a negative 3 and a negative 4. If I condense them, it goes to positive, and that I can find. But individually, you can't. So don't condense it first.
Oh, okay.
Does that make sense? Yeah. Don't condense it, because it could eliminate a negative that you actually can't use. I don't know how often that will happen, but it's possible. Okay, so last one, and then I'm going to go back to that warm-up and let you guys do it. Okay, so first thing I would do is what? I can condense, right? But before I combine them, they have to be the same log. So I have to get rid of that 3 on the front. How do I get rid of some number on the front of it? It becomes the exponent. So this 3 is going to come up here. So I get 3 equals log of 8 plus log of x to the third. Now condensing when it's addition is what? Multiplication. So log of 8 times x to the third. With me so far? So what's the base on the log? 10. So I got to get this in exponential form. I've condensed it so that it's 1 log, but now I've got it in exponential form. So the 10 comes over, picks up the 3, and the log drops off. I can, yeah. So there's a couple different ways to do it. You can either go straight to the cube root, right? Or you could simplify and then cube root. So let's say we cube root both sides. I have to cube root the 8 and the x to the third. And then the cube root of 10 to the third, which becomes 10 equals, what's the cube root of 8? 2x divided by 2, and x is 5. So that's one way to do it. If you didn't catch the cube root there, so if I'm here, and you actually kept going, so this would be 1,000 equals 8x to the third. And if I wanted to get the x by itself, what would I do? Divide by 8. And you have your calculators to help you, but 1,000 divided by 8 is 125. And then at this point, you'd have to cube root, right? In order to get rid of the cube, I would cube root both sides of the equation. And the cube root of 125 is 5. So either way, you get it, okay? And then I would check to make sure my answer is right, but I'm not going to have an extraneous root here. So the extraneous roots come from quadratics if I have x squareds and I'm factoring. All right, so let's condense it first, right? I got to get those 2 logs down to 1, and it's addition, which means what? Multiplying them together. So I'd get log base 4 of x minus 1 times 3x minus 1 equals 2. Then what? Perfect. So I can either FOIL out the 2 binomials right on the inside first, and then put it in exponential form, or exponential form and then get the binomials. It doesn't matter which one. So if I do this first, 4 to the second equals x minus 1 times 3x minus 1. This is 16 equals, and then I would first 3x squared. Outer, inner, last. 3x squared minus 4x plus 1. And then I would move the 16 over. As soon as you see the squared and the non-squared, you should know you're going to end up factoring. Okay, then comes the fun part, right? So there's 2 ways to factor this. How many of you are horrible at factoring if there's a number at the front? Be honest. Okay, so there's 2 ways to do it. One is trial and error, right? I could do this and this. And there's only so many options of 3x. It's going to be 3x and x. But then 15, I can do 1 and 15 or 3 and 5. And it's negative, which means one's going to be positive, one's going to be negative. So if I did negative 1, positive 15, I end up with outer and inner is 45 minus 1. And I need it to match this 4. So that's not going to work. So then I can switch them. This would be 1, this would be 15. And now I've got 3 and a negative 15, negative 12, still not going to work. So the other options are 3 and 5. 3x times 5 is 15x, minus 3 is 11x. That one doesn't work, so I switch it, and I get 5 and 3. So this is 9x minus 5x, which is 4x, and that's the combination that works. So now I'm going to set each of these equal to 0. And solve. So 3x minus 5 equals 0. And x plus 3 equals 0. 3x would equal 5. X would equal 5 thirds. And x would equal negative 3. So those are the 2 possible solutions. But now I've got to check them. So if I plug it back in here, 5 thirds minus, and you can kind of do the mental math on it to just see if you're going to end up with a negative. 5 thirds is the same thing as 1 and 2 thirds. So 1 and 2 thirds minus 1 gives me a positive number. That's okay. And then 5 thirds times 3 is 5 minus 1. That's still a positive number. So this number's okay. If I check this one in there, negative 3 minus 1 is a negative 4. And I'm not going to be able to find log of negative 4. So I rule this one out, and I keep the 5 thirds or the 1 and 2 thirds as the only possible choice. Questions? Okay, the other way to factor this, because some people are kind of bad at the factoring when there's, so if I take this, then the other way to factor when there's a number on the front is multiply the first term times the last term. So 3 times a negative 15 is negative 45. And then find the factors of that sum to the middle term. So this would be negative 9 and positive 5. And then I plug those 2 numbers in the place of this one. So negative 9x plus 5x minus 15. And then I've got 4 terms, and I can factor by grouping. So I take out the 3x, and I get x minus 3. Take out the 5x minus 3. And then what's in the parentheses gets grouped together. And the 2 terms that are left outside the parentheses also get grouped together. So it doesn't matter which way you factor it, but there's 2 ways to factor when there's a number in the front. So use whichever one works.